You are listening to lesson 2.4. We're going to try to apply what we've done with some derivatives to these concepts of position, velocity, and acceleration. Those of you who've done some physics may have already been familiar with these terms. The position function is like distance, so it gives the location of an object at time t. The notation we use for position, unfortunately, is quite different. Sometimes it's s, or sometimes you use x to represent a horizontal component, or y for the vertical component. But the velocity, we should know, is the rate of change of position. So I don't know, back in the good old days, we had something like this, remember? This was the average rate of change, or average velocity. I'm looking for now the instantaneous rate of change for calculus, so which means I want to take the limit in front of it. And we know that the limit in front of it represents what? It's a derivative. So therefore, velocity here is really the derivative of d dx, or d dt in this case, of the position function, s of t. Okay? So to go from position to get to velocity, we take the derivative, or we differentiate. And then for those of you, once again, in physics, you knew that acceleration was the change in velocity over the change in time. I want the instantaneous one, which is the limit, which means it's the derivative. So notice here that the acceleration, then I'll write it up here, a of t would be the derivative of, that's right, v of t. So to get from velocity to go to acceleration, we have to differentiate that again. Good. Some other things you might need to know. The initial position, of course, is when t equals 0, so that's just denoted by s sub 0. Initial velocity, v sub 0. Speed, now being careful, velocity is a vector, so it's a number along with a direction, where speed is just the number, so we just need to take a look at the absolute value of velocity. Okay, so don't worry about the sign. Then we have these terms called displacement and distance. What's that? Well, displacement is the net change in position. It's the final position minus the original. So if I were to draw me walking along this line, if I started here and went boop, and then wait, I stopped and I went back boop, and then I went back boop, like this, then the displacement is this distance from here to here. It's the difference between the starting, or the ending, sorry, and the starting. Yet total distance is the actual distance I traveled. So that would be taking this point, or this this piece here in green, plus this piece here in green. Oops, I wanted to use a different color. This piece in blue. Okay, and it's distance, so I don't really care about direction. I'm just looking at the absolute values of the distance. And then I have to add to that also this piece in yellow. So all three of those pieces added together, once again, the absolute value of those distances, that would be the total distance. Okay? And we'll take a look at an example here. We have one in-depth example, I think. Oh, no, sorry. One simple one, and then one in-depth one. All right, so just practicing with the velocity acceleration. How do we find that if we're given the position function? Yep, velocity, once again, is just the derivative, d dx, or in this case, d dt, because t is our variable, of the position function. So I want to find the derivative of t cubed plus t. We'll use the power rule, 3t squared plus 1. Done. Acceleration, once again, is the derivative, d dt, of velocity. And so I'll take my velocity function here, which is 3t squared plus 1. I'll take the derivative, that becomes 6t. And then the derivative of 1 is, don't do this, don't say plus 1. It's plus 0, or of course just nothing. Okay, so now I want you to use this more complicated position function. This function represents an object that's moving on a horizontal line. So think of here's a horizontal line. It has some starting position, and then it's moving either to the right, or to the left, or to the right and left. Whee! Okay. I asked, what is this starting position? That's a good question. Oh, that's the first question. What is the initial position? How do I find initial position once again? That's when the time is equal to 0. So I want the position at time t equals 0. I'm going to plug it into my expression, and hopefully you see that the answer is 24. So I guess my initial position here is 24. I guess 0 is like way over here. This is starting. t equals 0. I'm at a distance 24 away from, I don't know, the origin. Okay? Good. What is the velocity of the object at t equals to 1 second? So once again, velocity I need to find by taking the derivative of position. So here's my position function. Let's take its derivative. Derivative of t cubed is 3t squared. 3 times 16, that's 48. 48t squared. Once you do more of these, you can get faster. You don't have to write down all the steps. Negative 72t, and then derivative of 24 is 0. Good. And then I want it at 1, so I'll plug in 1. 48 times 1 squared minus 72 times 1. That's negative 24. And our units here, oops, I should put down units. Feet per second. I forgot my units here, feet as well. Okay. What is that? I don't need this stuff clear. Okay, so what I know as at 1 second, this is negative 24, so it must be going to the left. So I must be traveling to the left right now. Okay? At 1 second, I asked you what a speed. Well, remember, speed is just the absolute value. Oops. Speed is equal to the absolute value of velocity at 1 second. So the absolute value of negative 24 is just positive 24, or 24 feet per second. Okay. All right, what else can I ask you for? Next page. What is the acceleration of the object? Okay, so really now if I want acceleration, I need to find the derivative of velocity. And what was my velocity equation again? 48t squared minus 72t. Okay, so the derivative of 48t squared minus 72t, which equals to 48, constant, ignore it, t squared, the derivative is 2t, so 2 times 48 is 96, and then that's just 72. And I want it at 1 second, so 96 times 1 minus 72. I think the number is 24. 24 seems to be my favorite number for this particular, lesson. 24 feet per second squared, or per second, right? Feet per second, either or. Good. Now, when is the object at rest? What do you think rest means? Yeah, it's not moving. So if it's not moving, the velocity is 0. So this represents where the velocity equals to 0. Okay, so what's my velocity function again? Yeah, it's 48t squared minus 72t. I want to make that equal to 0. I'm going to solve by doing some factoring. I see a factor of 24t I can take out. That's 2t minus 3. And then if I make this equal to 0, that's t equals 0. And over here I get t equals to 3 over 2. So at 0 seconds and at 1.5 seconds, this thing has stopped. So remember when I did that drawing earlier? That's too far. This drawing here. Let me try to do that again down here. So, here's the person. This is 0. Here's 24. That's where he's starting. We know at 1 second he was moving to the left, so we know he was going like this. Whee! This is t equals 0, right? And then we know he would have stopped at what time? At 3 halves. Okay, so we know he's moving to the left, and he's going to stop at 3 halves. Now, if you want to think about where the position is at 3 halves, so this is an extra. What is the position at 3 halves? I want you to actually evaluate that. So plug it into my position function, which is on the previous page, 16 3 over 2 cubed minus 36 3 over 2 squared plus 24. I'm going to get my calculator to do that because my brain is tired. Is that the excuse you guys use for your teachers too? Oh, I can't do this, I'm tired. 3 over 2 squared. Oh, I don't need that. Plus 24. Negative 3. Okay, so whee, all the way here to the position of -3. So remember, this is the position graph. And at -3, I know I'm going to stop because at this time it's t equals to 3 over 2, and I came to a rest. Okay, cool. Okay, I hope that makes sense because I think the next part is important. When is the object moving to the right, and when is the object moving to the left? Well, moving to the left meaning its velocity is negative, so I'll actually answer number 8 first. Moving left means velocity is negative, less than 0. And we know that it was moving to the left between, what, 0 and 3 over 2, right? By my diagram here, I know that it went from 24, position 24 to -3, so during those values. So when do you think it moved to the right? Well, moving to the right means when velocity is greater than 0. And in this case, probably when t is bigger than 3/2. Now the question is it forever or does it stop again? Well, how do we answer that? Well, we know that the object is equal to 0 or at rest at 0 and 3 over 2. Now remember what we did in pre-calculus days where if I asked you to solve for an inequality, we'd find the zeros, we'd plot the points, and then we do that sign analysis. I think in this case it'd be negative, positive. My fault. Positive, negative, positive. Right? Ah. So really then I should have had another region over here that's positive, so why did I not include that in here? Well, including t is less than 0. What? What does that mean? How can time be less than 0? So we don't want to include that here. Okay? So just think about the restrictions on this problem. We're only looking at time bigger or equal to 0. Okay? So we know, therefore, then this diagram, this guy probably turns around and it goes whee and goes forever and ever to the right. Okay? Now, for number 9, when is the velocity equal to 54? Well, then this is where you want to make the velocity equal to 54 and solve for t. So 48t squared minus 72t equals to 54. Uh-oh, these numbers look bad. Equal to 0. I'm going to say solve using the graphing calculator. Use the graphing calculator, or if you like the quadratic formula, do that too. And I'm actually not going to do this for you. I want you to try it. That's just review stuff. But I'll tell you the answers are about negative 0.549 seconds and also approximately 2.049 seconds. Okay, now once again, use the graphing calculator or the quadratic formula to double check. I don't think you can factor this one. Okay? All right, the last two questions are to help you figure out the difference between displacement and distance. So what is displacement again? Yeah, it's the final position, in this case 2 seconds, and subtract it from the initial position. So that's displacement. Meaning we have to put it into our S equation, so 16 times 2 cubed minus 36 times 2 squared plus 24. And we know our initial position was just 0 cubed minus 0 squared plus 24. So those 24s cancel out. What is this equal to? What is this equal to? 128 minus 144. That's just negative 16 feet. So really at 2 seconds, whoops, where's my diagram? At 2 seconds, I probably am somewhere here. T equals to 2 seconds because the starting was at 24. The ending here probably was, what was this? I think it was 8, right? And so the net difference between 24 and 8, the net difference, negative 16. That's the displacement. Okay? So let me just write this in context. The negative 16 means that the displacement is 16 feet to the left of the initial starting position. Okay. Now, once again, what's the difference between displacement and distance? Distance is, distance traveled. So I'm asking you for this one in blue, and I want the absolute value of that. So I don't care if it's negative. I just want the actual value, how many meters or feet you traveled, and I have to add that to this distance in purple. Right? Oh, maybe too far. I just want to go to 2 seconds. Erase. Up to 2. Okay? So that piece that's in blue, that would be, so the total distance would be the distance from the original to the time where you stopped. So 3/2 minus the original, and I want the absolute value of that. And then plus, after that, would be the piece in purple. Oh, I went too far again. Sorry. I wish I could have multiple screens. Yes, this piece in purple here, right? Purple. That goes from 2 to 3/2. So from 2s(2) to s(3)2. Those two pieces, and once again, I put the absolute value because I don't care about the direction. I just want to care about how far you traveled. We'll then be able to calculate. S(3/2), we calculated above, that was -3. And then S(0) was 24. S(2) we calculated above, I think was +8. Okay, and then -3. So our total distance here is 27. Our distance here is 11. So how about 38 feet? That's the total distance I traveled going not only to the left, but also to the right, from t = 0 to t = 2 seconds. Whew, that was a lot, but nonetheless, I'm hopefully trying to give you an idea of how you can apply this calculus and the ideas of instantaneous rate of change to an application of position, velocity, and acceleration. Okay? Take a quick break if you need, and then come back as I finish off the rest of the notes for lesson 2.4. So AP loves using graphs. So notice here I've given you a graph that models the position function of a radio-controlled modeled car. Woohoo! Bring me back to my days when I was 5 years old. Whee! Driving these radio-controlled cars. Answer these questions, please, and explain why. So notice this is a graph of S, which is distance or displacement over time. And if I ask you, what is the car going faster at A or B? When I'm thinking about faster, I'm thinking about speed or velocity. So, I don't want the actual value, but I want to compare that's right, the slopes. So which one is it that's going faster? Probably B. Why? Because the curve has a, steeper or a bigger slope, or a bigger positive slope, I'll say, at point B. Okay? Stopped. When the car stopped? Stopped, we learned from the previous example that velocity must be equal to 0. And that means that the displacement or distance or position did not change. That occurs where? Between C and D. So I'll say between C and D. Because the velocity, which of course is the slope of the position curve, is 0 between C and D. All right. Now, at which point was the car's velocity the greatest? You'd be thinking, oh, I'm looking at the slopes again. I think it's here. Careful. This slope is negative. If I asked you for the greatest velocity, it's still going to be the greatest positive slope. So the greatest would be B. I'll say Y because it has the greatest or steepest point. Remember, this is positive point. At which point is this car's speed the greatest? Now we can answer with E, because remember, speed is just the absolute value of velocity, so I don't care about the actual sign. So it would be E, and Y, I'll say because the absolute value of the slope of this position graph is greatest, right? The largest, don't care about the negative sign or the positive sign, it's the steepest slope, doesn't matter if it's going upwards or downwards, at point E. Okay. All right, and then one last example here before we call it quits for today. The vertical motion example. You've seen these before in physics, maybe even in your pre-calculus courses, where they throw up a ball and they say, hey, when does it come to rest on the ground? When is it at the highest point? What is the highest point? Remember all that kind of stuff? Well, we used to have to do it with either taking data points and graphing it out in physics. Remember doing those labs? Or in math, we had to find the vertex of the parabola, because that was the maximum. No more, because we can now use ideas of calculus to help you do these questions. So suppose we have this function, negative 16t squared plus 48t plus 160. That is a parabola. That is an upside down parabola. So think about this. Whee! Right? It gives the position in feet above the ground for a ball thrown in the air from the top of a high cliff. So there's you on the high cliff and the ball goes down. Whee! How would we find the initial velocity? Well, now, because we have the position graph, we can find velocity by taking the derivative. So we take the derivative, we get negative 32t plus 48. And then if I were to now plug in the, initial, right? So initial means time is 0. We're going to plug in 0, and then lo and behold, you get 48 feet per second. And for those of you who remember the physics formula, that, yes, becomes the coefficient of that linear term. Yes, yes, yes. At what time does the ball hit the ground? Well, if I want it to hit the ground, I want the position to be 0. So ultimately, let's make the position equation equal to 0. I think I can factor a negative 16 minus, 3t plus 10. Gotta do some more factoring here. Running out of batteries. Better do it fast. T minus 5, t plus 2, t equals to 5, t equals to negative 2. What? Negative 2? Remember, time has to be bigger than 0, so 5 seconds is good. Okay? And then, here's an interesting question. At what time does the ball reach its maximum height? Oh, that's of course when the velocity equals to 0. So I want you to make the velocity equal to 0. Negative 32t plus 48 equal to 0. 48 equals to 32t. And I'm rushing this because I'm trying to do this before my battery dies. But you'll find that this equals to 1.5 seconds. So after 1.5 seconds, it reaches the top, and then it goes down to the bottom.